This video is to demonstrate how to use the apparatus and collect your data for the refraction lab experiment. So we have our apparatus here. You'll be using a blue clear block that we are going to examine the refraction phenomena through. And you will need a protractor for measuring your angles, as well as a ruler for drawing straight edges and measuring some distances. And we will also be using our red laser that we used in previous experiments. So I've already started by setting up my page. I've drawn a normal line down the center, and I've drawn the corners of my block. I've also continued that line across the front edge. That's going to help me making my measurements later on when I need to verify the law of refraction. So just going to line my block back up, and I'm going to plug in my laser. So what I'm looking for in this experiment is my incident ray and my refracted ray. And I'm going to measure the angle of incidence and angle of refraction. So the angle of incidence is defined as the angle from the normal where the ray hits our surface. So this being the normal line here, my incident angle is this angle here. And right away we see something interesting happening inside the block. So we actually see two beams. One of them follows the original beam, and then the other one is bent at an angle. So the ray that is bent at an angle is the one that we want to focus on. This is the refracted beam. So the angle of refraction is, again, from this normal line to the refracted beam. So what's this second beam? Well, what's happening is part of the laser is actually skimming over top of the block. So what you're seeing is the unrefracted beam. So just as a quick sidebar, I have taken my laser and I'm pointing it at the wall. So you can see that it doesn't actually form a point, but instead it forms a vertical line. So when we aim our laser beam at the block, some of the light passes through the block, but some of the light passes over top of the block. And this will be useful later on. Unfortunately for this experiment, it is a bit of a nuisance. Now, back to the law of refraction. So before you make your measurements, one thing that I've noticed is that if I let go of my laser ray box, it tends to slide around. So if you're finding this is happening, you may want to take something heavy and just place it on top. I'm just going to use this tape measure and place it on top of my laser box to prevent it from sliding around so that it stays in place while I'm making my measurements. And what you want to do is aim the laser so that you have your incident ray aimed at the surface so that it passes through at the point of the normal line. And you're going to use your protractor to measure the incident angle and the refracted angle. So with these large protractors, if I want to measure this angle, so from the normal line to my refracted beam, I could place my protractor like this, but the block isn't actually wide enough to read off where the beam crosses over the protractor. So what I would recommend is instead you can take the ruler and lay it on top of your refracted beam and extend that line backwards behind the block. Then once you remove the block, you can continue that line forward, and then you can measure the refracted angle that way. And as for the incident angle, what we want to do is draw in that beam. And we do want to use a ruler, but it can be difficult to fit the ruler in while the laser is pointing at the block. So I'm going to use the same technique I used in our previous lab, and I'm just going to sketch in a few dotted lines along my incident beam. And then when I take the laser out of the path, then I can now use my ruler to draw a straight line. And I'm going to extend my refracted ray back to the interaction point here, or the boundary between where the block was and where the air was. So now I'm able to measure the angle of incidence, so that is this angle here, so that's theta I, and I'm able to measure the angle of refraction, so that would be theta R in this case. And you'll want to include this sketch with the appropriate beams and angles labeled. So you're going to measure the incident angle and the refracted angle. And then you're going to repeat this process 2 more times. So once you've taken your protractor, measured the relevant angles, you're going to put the block back in place and then bring the laser back and measure the angle of incidence and refraction for 2 more angles. So you could make a steeper angle like this. Again, notice we have the refracted beam here, and then you have the continuing incident beam. That's just the laser beam going over top of the block. You can also see a reflected beam over here. So we don't care about the reflected beam or this continuing beam. We just want to measure the refracted beam. And then you could go, again, at a different angle. And in this case, these 2 beams are a little closer together, so pay careful attention to which one is the refracted beam and which one is still the incident beam. So if you're not sure, the incident beam is the one that just follows along the same line as the beam that you're aiming at the block. And then the refracted beam will be at a slightly different angle. Moving on to the next part of the experiment, we want to look at something called the critical angle. So the critical angle is defined as when you get total internal reflection. And we aren't actually able to exactly measure the critical angle because that is the angle where if the laser were exactly parallel to the block, then it's the angle of refraction inside the block. And you can see when we line it up like this, we don't actually get any refraction. But what we can do is place the laser at nearly that parallel to, or nearly 90 degrees to the normal, and look for the refracted beam. So this is a tricky measurement to make because you want to make sure that the beam is crossing into the block at the normal line. And it's also pretty tricky to see the refracted beam. It does get quite spread out. So in this case now, I'm at a slight angle here, so it's not quite 90 degrees with the normal. And you can just start to see that refracted beam inside the block here. So this is going to be a more difficult measurement to make. And you want to measure, again, the angle of refraction. So from the normal to where you see that refracted beam inside the block. So you'll want to use the protractor to do this. Once again, the protractor is a little bit large. So if you're having trouble seeing where that line intersects the protractor, you can use the same technique as before. So use the ruler and sketch backwards where that line is, and then you can take the block out and extend the line back in. So you'll make a measurement of the critical angle using the protractor. Recall that the protractor has 1 degree divisions as well as smaller half-degree divisions. So you'll want to consider that in your reading uncertainty. I didn't mention this in the earlier part, but particularly in part C and part D, when the block becomes, or sorry, when the laser becomes a little bit harder to see because it's a little bit blurry, it's a little bit spread out, you may want to include additional physical uncertainty for this part of the experiment. And you'll also want to draw the incident beam. So I'm just going to do a few dotted lines and then fill it in with the ruler afterwards so that you can measure how close or how far off you were from 90 degrees when you measured your critical angle. So I want to measure this angle of incidence from the normal to see how close or how far off I was from 90. And if I extend this line back, then I'm measuring this angle of refraction, which is my critical angle in this experiment. And then you're going to use that equation of the critical angle relating to the index of refraction to calculate the index of refraction of the block. In the last part of the experiment, we are looking at the beam displacement when it is refracted through the block. So I've taken a clean sheet of paper here and drawn a straight line. And what I'm going to do is take my laser beam, so my unrefracted ray, and line it up with the line that I've drawn. Next, I'm going to place the block, trying not to bump anything out of the way. I'm going to place the block so that it is intersecting the laser beam. By the way, this little green light here is just a reflection from the camera, so you can ignore that for this experiment. And what I'm going to do is change the angle of incidence by rotating the block. And you can watch what happens to the light when it exits the block. And as I rotate the block, so I'm changing the angle of incidence here, you can see that the beam, when it exits the block, has deviated from its original path. Its original path being this dark line over here. So in this position, I'm going to quickly outline where the block is so that I can place it back if I need to. And I want to draw in a few more lines. So I'm going to draw in a line here to represent the surface so that I can also draw in my normal line when I remove the block. And we want to make a few measurements here because we want to verify equation number 5. So we want to verify whether the relationship between the displacement, so the distance from the original to the deviated beam, and the width of the block, so that is the width across the block here, related to a couple of angles. So one of them being the refracted angle, so looking at the refracted beam from the normal line, which I have yet to draw in, and then another angle called theta A, which is related to the incident and the refracted beam. So I'm going to just take the block out for a moment. And I want to draw in my normal line, which is going to be perpendicular to the surface. So using a ruler here. I've now drawn the line which is normal to the surface. And although you can't really tell from the video, I did use 2 different colored inks so that I could distinguish them afterwards. I'm just going to line the laser back up. And now I'm able to make the necessary measurements. If I can get the laser to stay still. There we go. So I can actually already measure the angle of incidence. So that is the angle from the incident beam to the normal line. But that's actually not required for this part. What I do want to measure is the angle of refraction, and I want to look at where the deviated beam ends up. So I would recommend using similar techniques to what we've done in previous labs and in previous parts of this experiment. So it can be tricky to get a ruler in here. I'm going to draw a few dotted lines where the deviated beam ends up. And I'm going to take my ruler and lay it on top in line with the refracted beam here. That way I can just extend this line forward and backwards. And now I have the line where my refracted beam is. So if I take my block out, then I can move the laser out of the way. So I've got this line here, which is my refracted ray. And then I have my deviated ray over here. And now I can measure the necessary angles. All right, so with the block out of the way and the laser out of the way, I've labeled all of the various lines here. So the block is outlined in blue with the normal line also drawn in blue. So that's the normal to the surface. And my incident ray is drawn in black, and then my refracted ray is drawn in pencil. So there are 2 angles that I need to measure. I want to measure the angle of refraction. So that is this angle here from the normal line to the refracted beam. And then the second angle I want to measure is this angle here. And that's what we called theta A for simplicity. And that is the angle between the refracted beam and the path that the incident beam was taking. So you'll need to use your protractor to measure these 2 angles. And because the protractor, again, has 1 degree divisions with half a degree small divisions, consider the reading uncertainty when measuring those angles. And then also you may want to add in any physical uncertainty due to lining everything up, drawing in the lines, estimating the center of the laser beam, and so on. And then over here, I've labeled the deviated beam. So this is the beam that exited out of the block, parallel to the incident beam. And I'm measuring with a ruler this distance here. So this is lowercase d. That is how far the beam was displaced. And then finally, you'll want to measure w, which is the width of the block. And you can measure those with a ruler. This one I would measure directly on the block. So measure on the block, not just from the sketch. And then this one here, measure with the ruler. So standard ruler would have centimeter divisions with small millimeter divisions. So you would have reading uncertainty for measuring that distance, and then you may want to include any additional physical uncertainty.